This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Today's question asks how many ways there are of tiling a 2x6 space with 2x1 tiles. So the space can be represented with 12 dots like this, and 2x1 tiles. Each tile can either go vertically or horizontally. So 3 examples of tilings are this, this and this. Notice that all squares are covered and there are no overlapping tiles. First, we will present a straightforward method for solving this problem. Then we will present a remarkable formula applicable to any rectangular space tiled with 2x1 tiles, and then we will give a detailed proof of that formula. The straightforward way to solve this tiling problem is to look for a recursive formula. So we let x subscript n denote the number of tilings of a 2x n space using 2x1 tiles. If little n equals to 1, then we have a 2x1 space, because 2x n equals to 1, we have a 2x1 space. And so there's exactly one way of tiling a 2x1 space using 2x1 tiles. So x subscript 1 is equal to 1. If little n equals to 2, then we're looking at a 2x2 space. So we've got a square 2x2 that we need to tile with 2x1 tiles. And there's precisely 2 ways we can do this. Either both tiles are vertical or both tiles are horizontal. A proof of this, if you wish, is that we consider the tile lying on this top left square. It can either go horizontally or vertically. If it goes horizontally, that just leaves these 2 points, and so the only way we can tile them is with another horizontal tile here. Conversely, if the very first tile is vertical, that leaves these 2 points, and so the second tile has to also go vertically. This means x subscript 2 equals to 2. When subscript n is equal to 3, then we start our recursive formula. Again, just like in the proof of the x2 case, we look at our very first tile, so to speak, the tile going in our top left corner. Either it can go vertically or it can go horizontally. This gives us 2 cases, case 1 and case 2. In case 1, if our very first tile is vertical, that leaves a rectangle 2 by n minus 1 ways of tiling. So in this case, we're left with a 2 by 2 square. So in case 1, we have x2 ways of tiling this, where x2 is equal to 2. In case 2, when our first tile was vertical, then we must also have a vertical tile below it. And this means that the remainder of the tiling is based on how do we tile a 2x1 rectangle. So there are x1 ways of tiling it in the second case. In summary, for a 2x3 grid, the number of tilings is given by x1 plus x2. The way we explain that is essentially the way it's done in the general 2x n case. In the 2x n case, there's only 2 possibilities based on our tiling in the top left corner. Either we've got a vertical tile or we have a horizontal tile. If the tile is horizontal, then the tile below it must be horizontal too. In this first case, we're left with how many ways of tiling a 2x n-1 grid, and that's of course given by x subscript n-1. So the number of tilings for a 2x n grid is equal to the number of tilings in a 2x n-1 grid, corresponding to this case, plus the number of tilings in this case, and that's x of n-2, because we're left here with a 2x n-2 grid. Recall from the previous page that a 2x1 grid can be tiled in one way and a 2x2 grid can be tiled in 2 ways, and in general a 2x n grid can be tiled in the sum of the number of tilings for a 2 by n-1 grid plus the number of tilings of a 2 by n-2 grid. So with these two starting points, we can then apply this formula recursively. Precisely, we can write n along the top here, 1, 2, 3, 4, 5, 6, x of n, 1, 2, and then after this point, this number is simply the sum of the previous two numbers. So 2 plus 1 gives us 3, 3 plus 2 gives us 5, 5 plus 3 gives us 8, and 8 plus 5 gives us 13. We were asked how many ways there were of tiling a 2 by 6 grid, so we see that the answer is 13. As an aside, it's pointed out that this corresponds to the Fibonacci sequence. Recall that the Fibonacci sequence is defined by the same recurrence relation, f of n equals f of n minus 1 plus f of n minus 2. Of course, for a recurrence, the actual sequence depends on the initial values. For our tiling problem, we started with 1 and 2. For the Fibonacci sequence, there's actually three common choices. You could start with 0 then 1, leading to this sequence here. You could start with 1, 1, leading to this sequence here. Or you could start with 1, 2, leading to this sequence here. And in all three cases, they happen to contain our tiling x of n number here. There's actually an amazing formula that tells us how many ways we can tile a, well in general, an m by n space when m times n is an even number, but we'll just consider the special case of a 2m by 2n space for simplicity, but the general case is very similar to this. And the formula says a 2m by 2n space can be tiled with 2 by 1 tiles in this many ways. 4 to the power of mn, m and n determine the size of our rectangular grid. Then we've got two products here. One is the product over j going from 1 to m being this dimension. The other one is k going from 1 to n being this dimension here. And inside the products, the things we multiply together are cos squared j pi on 2m plus 1 plus cos squared k pi on 2n plus 1. It's really remarkable because these terms in here are not integer valued, but somehow this total product ends up being an integer, corresponding precisely to the number of tilings of a 2m by 2n space with 2 by 1 tiles. For today's question, we had a 2 by 6 space, so that means m equals to 1 and n equals to 3. Substituting these values in here gives us 4 to the power of m times n, 1 times 3 is 3. And then we've got a product of j equals 1 to 1, so we just take j equals to 1 here. We have a product of k going from 1 to 3, so we've got three terms here, 1, 2, 3. In the first case, j is 1, k is 1. So we get cos squared pi on m is 1, so pi on 3, plus cos squared k is 1, pi on n is 3, so on 7. Cos squared pi on 3 plus cos squared pi on 7. The next term, or the j remains 1, so this term will always be the same. We've got cos squared pi on 3 here, here and here. And the second term, k, increments 1, 2 and 3. So the first time we've got pi on 7, then 2 pi on 7, then 3 pi on 7. Using a calculator, we can evaluate this. 4 cubed is 64. Cos squared pi on 3 is a quarter. Cos squared pi on 7 is approximately 0.8117. Cos squared pi on 3 the same. Cos squared pi on 3 the same. Cos squared 2 pi on 7 is approximately 0.3887. And cos squared 3 pi on 7 is approximately 0.0495. And if we compute this, remembering that the answer should be an integer, so rounding it off, we have a loss of precision here by only keeping 4 digits after the decimal point. We get the answer 13. If we had computed these values exactly, then this answer would be exactly 13. If you do it by a calculator, you might have to slightly round it off. This is indeed the answer we got via the simpler method. The advantage of this method is it works for arbitrarily large rectangular spaces. In the previous formula, it might be extremely surprising to see cos terms. How can trigonometric functions appear in a tiling problem? The short answer is that the cos terms come from eigenvalues of a large matrix in 2x2 block diagonal form. A slightly longer answer is that first we compute what's known as a generating function. Each term in the generating function tells us how many tilings are possible in a certain arrangement. This generating function can be expressed in terms of something known as the Pfaffian of a particular upper triangular matrix. The Pfaffian is just the same as the square root of the determinant of a corresponding skew-symmetric matrix. If you have an upper triangular matrix, which is 0 along the diagonal, then you can simply fill in the lower triangular part of it to make it a skew-symmetric matrix. Computing the determinant of that skew-symmetric matrix and taking the square root gives you by definition the Pfaffian of the upper triangular matrix. If you then perform a similarity transformation on this skew-symmetric matrix, you end up with a 2x2 block diagonal matrix. Therefore, the determinant of the whole matrix is given by the product of these 2x2 block diagonal forms, and that's where the cos terms come from, the eigenvalues of these 2x2 block diagonal matrices. Let's now go through a proof of that remarkable formula. We will do it starting off looking at a particular case. For reasons that will become clear presently, associated to the problem of tiling a 2x4 space, we associate this corresponding upper triangular matrix. First, to every point in our 2x4 grid, we associate a number, 1, 2, 3, 4, 5, 6, 7, 8. The corresponding columns and rows of our matrix are numbered in the same way. We think of the column number as the destination, and we think of the row number as the source, where we can have a tile going from a particular point to a particular point. If we have a tile covering squares 1 and 2, then we can think of it either going from 1 to 2 or from 2 to 1, so to speak. However, we only want an upper triangular matrix here, and so therefore the destination will always be larger than the source. So a tile placed on points 1 and 2 will be considered as going from 1 to 2. And similarly, a tile that goes between 1 and 3 will be thought of as going from 1 to 3, from the smaller number to the bigger number. Sometimes looking at a more detailed problem actually makes the problem simpler, and in this case we're interested in not just the total number of tilings, but we also want to know how many vertical tiles there are versus horizontal tiles in each particular tiling. It will hopefully become clear later how this works, but we use the variable z to denote a vertical tile, and we use the variable z prime to denote a horizontal tile. So for example, if we have a tile from 1 to 2, remember our convention from the smaller number to the larger number, a tile from 1 to 2 would correspond to from 1 to 2, this position in our matrix, and a tile placed from 1 to 2 is going to be vertical, so I put a z there as opposed to a z prime. We would use a z prime for a horizontal tile, so indeed we could have a tile from 1 to 3, which would correspond to this point here, from 1 to 3, and because it is horizontal, we're going to use z prime rather than z in this spot. In this way, we fill out this upper triangular matrix with all the possible tiles we can place here. I can have a tile from 4 to 6, so from 4 to 6 corresponds to this entry here, and because the tile from 4 to 6 is horizontal, we use Z prime to denote it. Similarly, the tile from 7 to 8 corresponds to from 7 to 8. It is a vertical tile, so we put Z in here. The one thing which is a little bit of a mystery is that sometimes we use a negative in front of a Z prime. We will see why we have to do this, and somewhat remarkably, everything works with the simple rule that if it appears in an odd numbered row, so in rows 1, 3, 5 or 7, we are going to use a negative Z prime. Whereas if it occurs in an even row, 2, 4, 6 or 8, we will use a positive Z prime. If you are aware of a recursive formula for the determinant, then you'll know that when computing a determinant of a large matrix, then you're going to alternate sign, plus minus plus minus. And we care about the determinant of this big matrix here when we fill it in, which will be explained later. But because the number of tilings is always positive, whenever we have a negative appearing in a determinant expression, we want to convert it to being positive, and these signs somehow magically achieve this. For now, it suffices to accept the basic rule that for every possible tile, we create an entry in this upper triangular matrix, and we use either Z or Z prime as to whether it is vertical or horizontal, and we put a negative sign if it occurs with a Z prime, with a horizontal tile, in an odd numbered row. If you compute the determinant of a skew-symmetric matrix, you'll find that you can express it as the square of a polynomial of the upper triangular entries of that skew-symmetric matrix. And the Pfaffian is simply that polynomial. Whereas a determinant can be written as the sum over all possible permutations of the rows, the Pfaffian, we use only certain permutations. In the 8 by 8 case, we think of the numbers 1, 2, 3, 4, 5, 6, 7 and 8 as forming a set, and we're interested in all permutations, so we denote a permutation by k1 to k8, where each of these k's takes on one and only one of these 8 values, such that all 8 are used. We could have k1 equals to 1, k2 equals to 2, etc. We could have k1 equals to 8, k2 equals to 7, k3 equals to 6, etc. But we're interested in only those permutations that additionally satisfy these two rules here. The first rule is that if we consider, if we break these up into pairs, k1, k2, k3, k4, k5, k6, k7, k8, if we break them up into pairs, the first one has to be smaller than the second one. So there are 4 conditions here. And remember, this is reminiscent of when we formed our upper triangular matrix on the previous page from a tile going from a point to a point. We wanted it to go from the lower number to the larger number. The other constraint we have is that the first number in each pair has to be in ascending order. So k1 is less than k3 is less than k5, which is less than k7. And roughly speaking, this corresponds to the ordering in which we specify our tiling. When we want to tile the grid, roughly speaking, we'll tile it from left to right. Well, this makes precise the order in which we want to specify our tiling. And indeed, it will be seen that every tiling can be represented by such a permutation in a unique way. And that's what we will explain next. The Pfaffian is the sum over all such allowable permutations, but with this sign here, where the sign depends on something known as the sign of the permutation, which we'll discuss later. And as hinted at before, we want every term in this sum to be positive, but because this term here might be sometimes be -1, that's why sometimes we need to introduce a negative sign into our original matrix to make sure that the whole product in here is going to be positive. It's somewhat remarkable that it works, but it does. So the claim is that every tiling can be represented by a permutation satisfying these rules here, and we'll demonstrate this now. This tiling here is represented by the permutation 1, 2, 3, 4, 5, 6, 7, 8. Indeed, we look at our permutation and we look at the terms in pairs. So 1, 2 says there's a tile from 1 to 2. 3, 4 says there's a tile from 3 to 4. 5, 6 says there's a tile from 5 to 6. And 7, 8 says there's a tile from 7 to 8. Similarly, if we're given this permutation here, it tells us there's a tile from 1 to 2. There's a tile from 3 to 5. There's a tile from 4 to 6. And there's a tile from 7 to 8. And last example, the permutation 1, 3, 2, 4, 5, 6, 7, 8 tells us there's a tile from 1 to 3, a tile from 2 to 4, a tile from 5 to 6, and a tile from 7 to 8, where the numbers, of course, are given by the numbers here. The two rules that we mentioned are, firstly, in any pairing, we have the smaller number first. And secondly, in terms of consecutive pairings, the first number in each pairing has to go in ascending order. So we see in the first number of each pair is 1, 3, 5 and 7, that's in ascending order. 1, 3, 4, 7, ascending order. 1, 2, 5, 7, ascending order. If we are given this tiling, for example, then we know to specify it as a permutation, we're going to start with the smallest point that has yet been described in our tiling, which would be 1 in this case, and the tile goes from 1 to 2, so our first pair will be 1 to 2. We've used points 1 and 2, so the next smallest point available to us is 3, so we specify the tile that's on point 3, and the tile on point 3 goes to point 5, so 3 to 5 is our next entry in our permutation. Then we look for the smallest number not yet used, which will be 4. That gives us the start here, and the tile that covers 4 also covers 6, so 4 to 6 is here. The smallest number not yet used is 7. The tile at 7 also covers 8, 7, 8. It should now be intuitively clear that any tiling can be represented by a permutation satisfying the ordering rules we described before. Now, some permutations satisfying the ordering rules might not correspond to a valid tiling. For example, if we had a permutation where we needed a tile to go from 1 to 4, that's clearly not possible. However, the way we've arranged our matrix means when we come to compute the Pfaffian, any permutations that do not correspond to a tiling, we will end up with a 0 term in the Pfaffian and they won't count for a valid tiling. A Pfaffian, just like a determinant, is computed over various permutations of the elements of the matrix. Conceptually, to compute the Pfaffian of this particular matrix, we need to sum over all possible permutations that satisfy the rules for the Pfaffian, based on the ordering, you may recall. So for example, for this possible tiling, we have associated to it this particular permutation, and for this particular permutation, the term in the Pfaffian, this part here, is computed as follows. First, the sign term is going to be equal to 1, because we don't need to make any changes to the permutation 1, 2, 3, 4, 5, 6, 7, 8 to bring it equal to the standard arrangement in ascending order 1, 2, 3, 4, 5, 6, 7, 8. So that's equal to 1, and we'll explain this sign thing a bit later. Next, we have the product of 4 elements of this upper triangular matrix here. These elements are given by the one at position K1, K2, the one at position K3, K4, the one at position K5, K6, and the one at position K7, K8. With this particular permutation that corresponds to this tiling, K1 is 1, K2 is 2, etc., K8 is 8. And so therefore the 4 terms we care about are the term at 1, 2, At 1, 2 we have a z. We care about the term at 3, 4. K3 to K4 is 3, 4. The coefficient at entry 3, 4, 3, 4 is again z. The term for K5, K6 corresponds to the entry at 5, 6, which again is z. And the term at K7, K8 corresponding to the entry at 7, 8, 7, 8 is again z. So this term in here, corresponding to this permutation, equivalently to this tiling, gives us a z to the power of 4. What this tells us is that this particular permutation corresponds to a valid tiling, because this is non-zero, and moreover, that this valid tiling uses 4 vertical tiles, because Z represents vertical tiles and we need 4 vertical tiles, and 0 horizontal tiles, because there's no Z prime term here. Or equivalently, we can think of it as Z prime to the power of 0, corresponding to 1. So 4 vertical tiles, 0 horizontal tiles, corresponding to this permutation here. Given any other permutation satisfying the ordering requirements, either it will correspond to a valid tiling, in which case this term will contain z to the power of something, z prime to the power of something else, where the two powers sum to 4 because we need 4 tiles, and depending on how many vertical versus horizontal tiles we have here, that will determine the power of z and z prime. If we had 2 horizontal and 2 vertical tiles corresponding to our permutation, then this matrix here ensures that we'd have z squared, z prime squared. If we had 1 vertical and 3 horizontal, we would get z to the power of 1, z prime to the power of 3. The sine term in here compared to the sine terms in here are such that we will always end up with a coefficient of +1 in each term of our Pfaffian. Although it's probably necessary to watch to the end of this video, then come back to this point later, we're beginning to see already that the Pfaffian is doing our job for us of counting the number of tilings. The Pfaffian automatically sums over all possible permutations, so it goes through every single possible tiling, and also some permutations that do not correspond to a tiling. For each possible permutation, the term in the Pfaffian will either be 0 if it is not a valid tiling, such as, for example, if our permutation started with 1, 5, that would mean we have to have a tile going from point 1 to point 5, and that's just not possible. So for a permutation with an illegal tiling, we get a 0 term here. And for a permutation corresponding to a valid tiling, we will get precisely z to the power of the number of vertical tiles used, and z prime to the power of number of horizontal tiles used. So this Pfaffian is counting for us the number of possible tilings and laying it out for us in terms of how many horizontal, how many vertical tiles we need. Now, of course, there might be more than one way of tiling this grid using 2 horizontal and 2 vertical tiles. So we will have several different permutations, each of which gives us a z squared, z prime squared. So if we add them up and we get, for example, 3 z squared, z prime squared, that means there are precisely 3 tilings with 2 horizontal and 2 vertical tiles in them. Computing this Pfaffian by hand is essentially the same as systematically going through every single possible tiling and adding them all up. The only way for this to be mathematically useful is if there is some other way of computing the Pfaffian rather than computing this sum directly. And we will find that that is indeed the case, and that gives us our amazing formula that we introduced earlier. Recall that the Pfaffian is computed directly by summing over all possible valid permutations. We give another example of the computing the term in the Pfaffian associated to a particular permutation. We will consider this particular permutation here. Directly from the formula for the Pfaffian the term corresponding to this permutation is the product of the sign of this permutation multiplied by the element of the matrix in the 1, 2 position times the element of the matrix in the 3, 5 position times the element in the matrix in the 4, 6 position times the element in the matrix in the 7, 8 position here. As will be explained presently, the sign term of this permutation is -1. The element in the 1, 2 position is z, 1, 2, z, 3, 5, 3, 5, negative z prime, 4, 6, 4, 6, z prime, and 7, 8, 7, 8, z. This gives us, when we multiply this, this, and this together, this gives us z squared, z prime squared. So in the Pfaffian, we sum over all possible valid permutations. For this particular permutation, we get this term appearing in the Pfaffian. That's what happens mathematically, but why do we care about getting this term here when we compute the Pfaffian? Well, this term tells us that corresponding to this permutation, we have a valid tiling using 2 vertical tiles and 2 horizontal tiles. And indeed, if we take this permutation here and associate the corresponding tiling to it, so we have a tile from 1 to 2, a tile from 3 to 5, a tile from 4 to 6, and a tile from 7 to 8, we find that indeed we've used 2 vertical and 2 horizontal tiles. This matrix here was chosen to obtain this result here. Recall that this matrix was constructed simply by saying, because a tile from 1 to 2 will be vertical, we therefore put a z in the position 1 to 2 in the matrix. And similarly, because a tile from 3 to 5 would be horizontal, we essentially put a z prime in the matrix at 3, 5, and so forth. The only trick is that some of these entries have to be negative if we want to make sure that every term in our Pfaffian is either 0 or has a coefficient of +1. The reason is that the sign of the permutation might sometimes be negative, like it is here, and in this case we must have that when we compute this product here, we end up with a -1 to cancel out the -1 coming from the permutation, making the overall coefficient +1. There is a nice argument in the original paper that explains why this trick works, and I've written the reference to that paper in the description of this video. For those that are curious, the way to compute the sign of a permutation is to ask how many swaps are required to bring this into the standard permutation of 1 to 8 in ascending order. If the number of swaps required is odd, then the sign will be -1, while if the number of swaps is even, the sign will be 1. In this particular case here, we see that we only have to swap 5 and 4 to bring this into the standard form of 1, 2, 3, 4, 5, 6, 7, and 8. One swap is an odd number of swaps, so the sign of this permutation is -1. For some permutations, it might be that you need a different number of swaps to your friend to bring it into standard form, but if you required an odd number of swaps, then your friend will also have required an odd number of swaps. And similarly, if you required an even number of swaps, your friend would also have required an even number. Therefore, the sign of a permutation is a well-defined quantity. -1 if an odd number of swaps are required, and +1 if an even number of swaps are required. For the case of a 2x4 grid, we can work out what we expect the Pfaffian to be. We go through all possible tilings, and it turns out that in the 2x4 case, there's only 5 possible tilings. For each tiling, we write down z to the power of the number of vertical tiles used times z prime to the power of the number of horizontal tiles used. 4 vertical tiles, z to the 4. 2 vertical, 2 horizontal, z squared, z prime squared. Same here, same here. 2 vertical, 2 horizontal. 4 horizontal means z prime to the power of 4. And the Pfaffian is simply the sum of these 5 terms here, which gives us z to the 4 plus 3z squared z prime squared plus z prime to the 4. This is what's known as a generating function because we care about the coefficients. The coefficients tell us the number of tilings we can have. With 4 vertical tiles, we have 1 tiling, the coefficient in front of z to the 4. With 2 vertical and 2 horizontal tiles, there are 3 possible tilings, this, and this. And with 4 horizontal tiles, the coefficient here is 1, so there's only 1 possible tiling here. If we just want to know the total number of tilings, that's easy. Just substitute 1 for both z and z prime. If z is 1, z prime is 1, then each term here, the z's end up being a 1, so we just get 1 plus 3 plus 1. In other words, there are 5 different tilings. So once we can compute the Pfaffian, we can easily find the number of tilings just by substituting z equals z prime equal to 1. We computed this Pfaffian by hand just to gain a better understanding. The aim, of course, is to come up with a mathematical expression for the Pfaffian valid for any sized grid here. To algebraically compute the Pfaffian, we will use the fact that the Pfaffian is the square root of the determinant of this matrix here, obtained by taking the upper triangular matrix, whose Pfaffian we want, and creating a lower triangular matrix such that the overall matrix is skew-symmetric. This of course means that we take the upper triangular matrix, we take its transpose and multiply everything by -1 to form the skew-symmetric matrix. Next we write this matrix in algebraic form, and it turns out that it can be written in terms of a Kronecker product and 3 different types of matrices. I represents an identity matrix, in this case a 4x4 identity matrix. A Qn matrix, so to speak, represents an n by n matrix, which is 0 along the diagonal, 1 along the superdiagonal just up from the main diagonal, and -1 along the subdiagonal just below the main diagonal. So Q4 is equal to a matrix with all zeros, a 4x4 matrix with all zeros except for 1 along the superdiagonal and -1 along the subdiagonal. The last matrix we need is, in this case, an F2 matrix. In general, an Fn matrix will have diagonal entries alternating -1, 1, -1, 1, and so forth. This generalization will work for any size grid, whereas at the moment we're giving a specific example for when m equals to 1 and n is equal to 2. The reason we used the Pfaffian before and the determinant now is because the formula for the Pfaffian involves a sum over certain permutations, and that allowed us to work out how to associate tilings with entries in the Pfaffian. But to compute the Pfaffian algebraically, it's a lot easier to work with determinants, which is what we do now. Indeed, to compute the determinant of a matrix, one way is to try to reduce this matrix to a diagonal form. Then the determinant is just the product of the diagonals. It turns out that we can almost do this, and by introducing such a similarity transform, rather than making this diagonal, we, roughly speaking, are going to be making it into a 2x2 block diagonal matrix, and from that we can still read off what the determinant will be. In terms of specific details, recall that the Kronecker product allows us to create a fairly big matrix out of 2 smaller matrices in the following way. For every entry in the matrix on the left-hand side, we multiply it by the whole matrix on the right-hand side to get a submatrix in the final answer. So in this matrix here, the 1 here gets multiplied by this matrix here, 0, 1, negative 1, 0, to create this entry in here. The 0 here gets multiplied by this to give us a 0 block matrix in here, and so forth. So in this case, because we have 4 ones along the diagonal, we get Q2 repeated 4 times along the diagonal. That's the effect of this Kronecker product. Similarly, the Kronecker product down here works in the same way. For each entry in this matrix here, we multiply that entry by this whole matrix here to get a submatrix over here. Because this is 0, we end up with a 2 by 2 0 matrix in the top left corner. Because this is a 1 here, we get this matrix occurring in this location here. And because this is a negative 1, we get negative 1 times this matrix occurring in this location here. So Q4 times this F2 matrix here gives us this matrix here, where we see that the F2 matrix appears verbatim along this diagonal here, 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 and here, and it appears multiplied by negative 1 along this diagonal here, here, and here. The claim is that if we multiply this matrix here by Z, we will get the corresponding Z entries in this skew-symmetric matrix here, while if we multiply this matrix here by Z prime, we will get the corresponding Z prime entries in this matrix here. And this can be checked just by comparing where the entries are. So the red ones are Z and the yellow ones are Z prime. For example, there are 4 Zs, 1, 2, 3, and 4, corresponding to 1, 2, 3, 4. Because we want a skew-symmetric matrix, we also have negative Zs occurring down here, corresponding to these 4 negative Zs here. While for Z prime, we have got negative Z prime, negative Z prime, Z prime, negative Z prime, Z prime, corresponding to the ones underlined in yellow here. And similarly, below the diagonal, we've got the skew terms, so they differ by a sign by their symmetric counterparts. So where we had a negative Z prime here, we'll have a Z prime here. Negative Z prime here, Z prime here, and so forth. So we want to compute the Pfaffian because it is the generating function telling us how many tilings there are. To do that, we're going to compute this determinant here and take the square root. Because our strategy is to try to reduce the matrix to diagonal form, we need to compute the eigenvalues and eigenvectors of the whole expression. That's a little bit difficult, but we can compute the eigenvalues and eigenvectors for the 2 terms, and it turns out, again by some amazing property, that although the eigenvectors are not the same, there's enough similarity between them that we end up with a 2 by 2 block diagonal matrix and are able to compute the determinant from that. As a warm-up exercise, we first compute the eigenvalues and eigenvectors of just Q2 itself. To find the eigenvalues, we form the matrix Q2 minus lambda I, where I is the identity matrix with 1s along the diagonal and 0s everywhere, and lambda is a complex number. We then compute the determinant of this matrix, and by definition, a value of lambda, which makes this determinant 0, is an eigenvalue of this matrix here. So Q2 minus lambda I is just the matrix Q2 where we add negative lambda to all the diagonal terms. So we have negative lambda, 1, negative 1. We take the determinant. For a 2 by 2 matrix, the determinant is the product of these 2 elements minus the product of these 2 elements. So negative lambda times negative lambda gives us lambda squared. 1 times negative 1 gives us negative 1. So we've got lambda squared minus negative 1 gives us lambda squared plus 1. This is equal to 0 when lambda is plus or minus the square root of negative 1, which we denote by I. To find the eigenvectors, we solve this following equation where we've replaced lambda with an eigenvalue, and so the vector x we find here will be the eigenvector associated to that particular eigenvalue. For the eigenvector associated to the eigenvalue lambda is equal to I, we solve this equation here. This matrix here is given by this matrix here. We multiply it by a vector and we want to get the answer 0. Evaluating this multiplication here, so this times this plus this times this gives us this, and this times this plus this times this gives us this. We want both these entries here to be 0. Any solution we get can be multiplied by a scaling to get another solution, so we are free to pick one of these two values, either x1 or x2, and solve for the other one. If, for example, I choose x1 to be I, then I times I is -1, multiplied by -1 gives me 1, so x2 must be -1 to make this term 0. So I try -1 here. I double check that this will also make the second entry 0, -I minus I times -1 gives me -I plus I, or 0. So this is indeed the eigenvector up to scaling of the eigenvalue I. Similarly, to find the eigenvector associated with the eigenvalue -I, we solve this equation here and find that I1 up to scaling is the associated eigenvector. For a large class of matrices, normal matrices to be precise, and skew-symmetric matrices belong to this class, the power of finding the eigenvalues and eigenvectors is that we can essentially represent the matrix in a simplified form. Precisely, if we take each eigenvector, we normalize it so that it has got unit length, and arrange the eigenvectors into a matrix so that each column is a unique eigenvector. Then we get a unitary matrix. Think of it like a rotation. And moreover, if we take this unitary matrix, whose columns are the normalized eigenvectors, and we take our original matrix, Q2 in this case, and form U2 inverse times Q2 times U2, we will get a diagonal matrix whose diagonal entries are precisely the eigenvalues corresponding to each of the eigenvectors. So for this eigenvector here, the corresponding eigenvalue is I, and for this eigenvector here, the corresponding eigenvalue is -I. I've skipped over a technicality. Here everything works nicely because the eigenvalues were unique. If you have a multiple eigenvalue, then you have to work a bit harder to find some orthogonal eigenvectors that span that eigenspace. Right, now though, all that matters is that somehow we were able to find this matrix U2 that has got this property here, U2 inverse times the matrix we care about, Q2, times U2 has got this diagonal form here. This will help us compute the determinant. We also need to do the same thing for the matrix Q4. And if we need to do Q4, then we may as well do Qn in the general case. So consider the matrix Qn, which is n by n, has got 1s along the superdiagonal and -1s along the subdiagonal. How can we find the eigenvalues and eigenvectors? Now in general, finding the eigenvectors of an n by n matrix where n is large is extremely difficult, even with a computer. But this matrix here has got a very special structure, and it turns out we can find the eigenvectors and the eigenvalues in closed form. The way we do this is by just writing out directly the equation for the eigenvector and noticing that it can be written as a recurrence relation, as we will go through now. By definition, an eigenvalue-eigenvector pair is a solution to this equation here, where lambda is an eigenvalue and x is the associated eigenvector. On the left-hand side, we've got Qn times the vector x. If I write the vector x here, x1, x2 down to xn, then when we form this product here, Qn times xn, we've got 0 times x1 plus 1 times x2 plus zeros times all the rest of the x's. So we just get an x2 term corresponding to this term here. This equation is the first row of this equation here. On the left-hand side, we see we just have 1 times x2 or x2. On the right-hand side, we've got the scalar lambda times x. So the first entry will just be lambda times x1. So we've got x2 equals lambda x1. Bringing this term to the other side, we get negative lambda x1 plus x2 equals to 0, the first row of this. The second row of this equation is found by observing it'll be negative 1 times x1 plus 0 times x2 plus 1 times x3 plus 0 times everything else here. So that should give us a negative x1 plus x3, negative x1 plus x3. And that's equal to lambda times this expression here. The second row will be lambda times x2. Bring it to this side, negative lambda x2. So the second row gives us this. And in general, we find that we have a simple pattern occurring, except for the very first row and the very last row. But a small trick is to introduce two more x terms, an x0 and an xn plus 1 term, make them both 0, and then every row here can be written in this form here, where little n now goes from 1 to big N. When little n is 1, then n minus 1 is 0, x of 0 is 0, so this term disappears. When n is 1, we've got negative lambda x1, plus x2, so n equals to 1 corresponds to this term here. And similarly, you can show that when n is equal to 2, we get this term here. When n is equal to big N minus 1, we get this term here. And when n is equal to big N, we get this term here, keeping in mind that x of big N plus 1 is equal to 0. What we need to do is try to solve this recurrence relation subject to these two constraints here. There may or may not be a solution to this recurrence equation subject to these two constraints here. If there is not a solution, that just means the value of lambda is not an eigenvalue. Conversely, if lambda is an eigenvalue, then there will be a solution to this set of recursive equations here, satisfying these conditions here. If we ignore the constraints, x0 and x big N plus 1 are equaling 0, if we ignore those two constraints or boundary values and focus just on this recurrence relation here, this is a linear finite difference equation and it will always have solutions, and there's a standard trick for finding all solutions. First, we look for solutions of a very specific form. We ask if there are any solutions of the form xn is equal to some fixed scalar to the power of n. If there is such a solution, then it must satisfy this equation here, obtained simply by substituting this into here. If this is true, then we can factor out, and this is true, by the way, for little n being equal to any integer. We fix a particular integer n, so to speak, and we can factor out the term phi to the power of n minus 1, and if we factor this out, then this becomes -1 minus lambda times phi plus phi squared. And if this is true, then this has to be true. From this, we see that either phi equals to 0, but that just corresponds to the 0 solution here, where all the x's are 0, and that's not very interesting. Or, for an interesting solution, if the scalar phi here satisfies this quadratic equation, phi squared minus lambda times phi minus 1 equals to 0, if phi satisfies this, then xn equals phi to the power of n will satisfy this linear finite difference equation. Being a quadratic, in general, there are two distinct solutions phi that will lead to solutions of this form here. The characteristic equation, simply replace phi with z. Z squared minus lambda z minus 1 equals to 0 has got two roots. One of them is lambda on 2 plus the square root of lambda on 2 all squared plus 1, and the other is the same thing but with this plus replaced with minus. This of course comes from the formula for the roots of a quadratic equation. Lambda, remember, is a fixed number, and for any given lambda we have now seen that we can find solutions to this equation here, but they may not satisfy the conditions of x0 and x of big N plus 1 both equaling 0. If there's a lambda for which there's a corresponding solution for which those two terms are 0, then we've found an eigenvector. But first, there's a small technicality. We can actually form solutions other than these solutions here, but in fact it turns out that all solutions, the most general solution in this case, will be of this form here, where we simply take the two solutions we found and add them together. We can also introduce arbitrary scaling factors to both solutions. The reason this works is because this equation is linear. I won't elaborate on this here, but because it's linear, it means that if you have found a solution, then any scalar multiple of the solution will also be a solution. And if you found two different solutions, then you can add them together and that will also be a solution. That's a consequence of this being linear. The fact that this is the most general solution is not overly hard to see. We can actually solve linear finite difference equations by hand simply by picking two initial values. If we choose a value, for example, for both x0 and for x1, then we can use this expression to generate x2. And then once we've got x2, we can substitute that back in and compute what x3 must equal, and so forth. So it's not hard to see that all solutions are obtained just by picking values for x0 and x1. Roughly speaking, this means that we have 2 degrees of freedom in here. If you want to be technical, it means the set of all solutions forms a two-dimensional vector space. Down here, we have found two distinct solutions, and so we have recovered our 2 degrees of freedom here. Changing the values of a and b are equivalent to changing the values of x0 and x1. The only time this breaks down is if the two roots here are the same. But provided lambda is not equal to 2i, we have two distinct roots, and this will work. We will see later that in all cases we do indeed have lambda is not equal to 2i, so therefore what we're doing here is perfectly valid. To summarize, the key facts are as follows. Firstly, if we have lambda being an eigenvalue and x of n being the elements of the eigenvector, in addition to having x0 equaling 0 and x big N plus 1 equaling 0, then the lambda and the xn's will satisfy this recurrence relation here. On the other hand, for any given lambda, we can always solve this recurrence relation. In fact, we get solutions of this form here, where we are free to choose A and B any way we like, but phi1 and phi2 are fixed to being these two numbers here, corresponding to be roots of the characteristic equation up here. And thus, what we really want to know is, can we find a lambda, and can we find A and B such that our solution has got both x of 0 and x of big N plus 1 equaling 0. If we have done that, then we have found an eigenvalue-eigenvector pair. Here are the solutions to our recurrence relation. Phi1 and phi2 depend on lambda. A and B are free for us to choose, the scalars. We want to know whether we can choose A and B so that x0 and x big N plus 1 are both equal to 0. For some values of lambda this will not be possible, for others we can do this. If we want x0 to be equal to 0, substituting little n equals to 0 in here gives us x0 equals A plus B, because something to the power of 0 is 1. So we require A plus B to be equal to 0, which means B is negative A. So first thing we do is we rewrite our solution in this form here. We get rid of B because now, at this point, we only care about solutions which also satisfy x0 is equal to 0. We have a second simplification, and we can see this in one of two ways. The first is that we just want x of big N plus 1 to be equal to 0. The constant A here is just going to scale the value of each of the x terms. So if the x term is already not going to be 0, then changing A won't help. And if it is already 0, then it doesn't matter what value of A we choose, it will remain 0. So the value of A doesn't matter, and we may as well just assume it's equal to 1. The equivalent way of saying this is that we know that eigenvectors are only unique up to scale, so we can therefore double the eigenvector, halve the eigenvector, it still stays an eigenvector, and so we may as well just take A equal to 1. This means that we now simplify our solutions. We throw out all the solutions, we just care about this particular solution here. This solution will satisfy x0 equal to 0, and we only want to know whether or not we can find a lambda, because lambda will change the values of phi1 and phi2. Can we find a lambda such that x at big N plus 1 is equal to 0? If we can, then lambda is an eigenvalue, and the solution here gives us the corresponding eigenvector. We only care about solutions of this form, and we want lambda to be such that x at big N plus 1 is equal to 0. So if this is equal to 0, that means this term has to equal this term, and we want that to be true when little n is equal to big N plus 1. So we want to find lambda such that phi1 to the power of big N plus 1 is equal to phi2 to the power of big N plus 1. Remember, lambda changes our quadratic equation, and phi1 and phi2 are roots of that corresponding quadratic equation. Dividing both sides by phi2 to the power of big N plus 1 means that this is equivalent to phi1 divided by phi2, all to the power of big N plus 1 is equal to 1. There are only n plus 1 possibilities for this equation to be true here. Indeed, phi1 divided by phi2 has to be an n plus 1th root of unity. The easiest way to write roots of unity are to use complex exponentials. Recall that e to the I theta represents the complex number that has got magnitude 1 and forms an angle theta with respect to the x-axis, where the y-axis are the imaginary numbers. In particular, e to the I 2 pi theta means we wrap around the circle once and come back to the real number 1. So e to the I 2 pi is equal to 1. So e to the I 2 pi 1 on n plus 1. If we were to raise that to the power of n plus 1, we end up with e to the I 2 pi n plus 1 divided by n plus 1, or e to the I 2 pi, or 1, and so we have indeed found an n plus 1th root of unity. And indeed all of them are found by choosing k to range from 0, 1 up to big N in here, as directly verified. Simply take this expression, raise it to the power of n plus 1, that will cancel the n plus 1 on the denominator, so we have e to the I 2 pi k, where k is an integer. That means we have gone a whole number of times round the circle, and hence this will always be equal to 1 if k takes on an integer value. Hence we have found all the possibilities for this equation here. Being n plus 1, we can have at most n plus 1 solutions. One of these possibilities does not correspond to an eigenvalue-eigenvector pair. Indeed, if k is equal to 0, this means that phi 1 divided by phi 2 is equal to 1. This means phi 1 equals to phi 2. And if we have that in here, if phi 1 equals phi 2, that just means x0, x1, x2, x anything is equal to 0. And so we have not found an eigenvector. We have simply refound the trivial solution that lambda can be anything and x can be 0 in the eigenvector equation, which we don't want. So we discard the k equals to 0 case, and henceforth we just look at the big N possibilities where phi 1 divided by phi 2 is equal to this number here, where k goes from 1 up to big N. For each value of k from 1 to big N, we ask, can we find a lambda? And since we're doing this for different values of k, we put a subscript k to our lambda so we don't get confused. Can we find a lambda k such that this ratio here is equal to this particular n plus 1th root of unity? If we can find a lambda such that this is true, then we have found an eigenvalue-eigenvector pair. Recall once again that phi 1 and phi 2 are the roots of a quadratic equation that depend on the value of lambda. To slightly simplify notation going forwards, I'm sometimes just going to write theta to stand for 2 pi little k on big N plus 1. This implies that I've chosen a value of k, I've fixed it, and I don't bother to represent it with a subscript k on theta. Precisely, I want to be able to find a value of lambda such that phi 1 divided by phi 2 is equal to e to the I theta, where theta is arbitrary. Once I can do this, I can then replace theta with 2 pi little k on big N plus 1, which is what I care about, and then find my corresponding eigenvalue lambda k. From before, here are our equations for phi 1 and phi 2 in terms of lambda. These are the roots of a quadratic equation that depend on lambda. We could solve directly. We want to find lambda such that phi 1 divided by phi 2 is equal to e to the I theta, and I can substitute in the two expressions for my phi 1 and phi 2 in here, and then just clear denominators and try to solve. But that's the slow, not so clever way. Instead, what we should do is make use of the fact that we know that phi 1 and phi 2 are the roots of a quadratic equation. Specifically, They are the roots of the quadratic equation z squared minus lambda z minus 1 equals to 0. Being the roots, in other words, it means that z squared minus lambda z minus 1 is equal to z minus phi 1 in brackets times z minus phi 2 in brackets. These are the two roots that make this 0. If we were to expand this out, we get z squared minus phi 2z minus phi 1z plus phi 1 times phi 2 and equate coefficients. We see that phi 1, phi 2 is equal to negative 1. The product of the two roots is equal to this coefficient here. And the sum of the two roots is equal to negative of the coefficient here. So for any value of lambda, we know that this will be true and this will be true always, due to the fact that phi 1 and phi 2 are roots of this quadratic equation here. So conceptually, we are solving this equation here, but by making use of these relationships here, we can get the answer much faster, which we do on the next page. To solve this equation here, first we make use of this identity. We multiply both sides of this equation by phi 1, phi 2. So we get phi 1 squared on the left-hand side and phi 1, phi 2 e to the I theta on the right-hand side. Phi 1, phi 2 is always equal to negative 1, so this becomes negative e to the I theta. We then take square roots. The square root of negative 1 is I. The square root of e to the I theta is just e to the I a half theta, because the square root is raising something to the power of 1/2. And then if something squared is equal to something, then there are always two solutions, plus or minus the square root of the right-hand side. If phi 1 is equal to this, then phi 2 is equal to negative 1 divided by phi 1, negative the reciprocal. And to take the reciprocal of this, 1 on I is just negative I. The negative then cancels with the negative 1 here. And the reciprocal of e to the I a half theta is just e to the negative I a half theta, because taking the reciprocal is the same as raising this to the power of negative 1. Given phi 1 and phi 2, to find lambda, the fast way is to make use of this identity here. Lambda is equal to phi 1 plus phi 2, so we just add these two solutions. Here the convention is that if I choose phi 1 to be positive this guy, then phi 2 is also positive this guy. Whereas the second pair of solutions, phi 1 would be negative this guy, phi 2 would be negative this guy. So when we add these two up, we get either both of these are positive, and we get plus I times, in brackets, this plus this, which is the same as 2i cos theta on 2. Recall that e to the I theta equals cos theta plus I sine theta. On the other hand, if we choose the negative solution for both phi 1 and phi 2, then we will get negative the same thing here. Therefore, we have, for a given theta, we have two possibilities for lambda, either plus or minus 2i cos theta on 2. Recall that we only care about lambdas for which the solution has got the n plus 1th term equaling 0. So for that, we need phi 1 on phi 2 to the power of big N plus 1 to be equal to 1. This means that the ratio phi 1 divided by phi 2 needs to be an n plus 1th root of unity. While there are n plus 1 such roots, given by this expression here, where k would go from 0 all the way up to big N, we don't want the k equals to 0, 1, because that will correspond to the 0 solution. Technically, there's an additional complication. If phi 1 equals phi 2, then there might be another solution to the finite difference equation, and we'll return to this later. It turns out that there's not, and these are all the solutions. For each value of k equals 1 to big N, we want to find a lambda such that this is true. From the previous page, we know that for each k, we've got two solutions, a positive solution and a negative solution. It turns out we just have to remember the positive solutions because the negative solutions are equivalent to the positive solutions, as we'll explain presently. From the previous page, we were able to solve this to find that for a given k, the solution is lambda k equals 2i cos pi little k on big N plus 1. With this choice of lambda k, we get that phi 1 is equal to this and phi 2 is equal to this. As k ranges from 1 to big N, we get n distinct values for lambda k. They're all different. If we recall, the lambda k correspond to eigenvalues of an n by n matrix. There are at most n eigenvalues of an n by n matrix, and so therefore we must have found all of them. This implies that the negative solutions must somehow correspond to these positive solutions. It turns out that we're going to need this calculation here for future use, so we go through it explicitly. If instead of choosing the positive solutions, we choose the negative solutions, then we get that lambda k is equal to negative 2i cos pi little k on big N plus 1. For each value of k, this lambda k must somehow be equal to one of the eigenvalues we found over here. So if we change coefficients, if we call this lambda k prime and this one lambda k, then for each k prime we need to be able to find a k such that the lambda k over here, defined this way, is equal to lambda k prime over here, defined this way. To do this, recall that cos of pi minus theta is equal to negative cos theta. So therefore, negative something times cos of something is equal to positive something times cos of pi minus that something. Factoring the pi out, we see that the k we need in this expression over here, because here we have 2i cos something, 2i cos something, to make this equal to this, we choose little k to be equal to big N plus 1 minus k prime. Another way of writing this is to say that the k we need satisfies k plus k prime equals big N plus 1. Indeed, from here, our k is equal to big N plus 1 minus k prime. So for any negative solution, we can find a corresponding positive solution over here. This means that the only unique solutions are the ones given over here, which we will stick with going forwards. To summarize, for the matrix Qn, which is an n by n matrix with 1 along its superdiagonal and negative 1 along its subdiagonal and zeros everywhere else, for Q of n we have found all its eigenvalues and corresponding eigenvectors. There are n distinct eigenvalue-eigenvector pairs, which we index by k, going from 1 to big N. The kth eigenvalue is given by 2i cos pi of k on big N plus 1. The corresponding eigenvector, which is only unique up to a scalar constant, is given element-wise by this expression here. Here, this denotes the nth element of the kth eigenvector associated with the kth eigenvalue, and it's given explicitly by this expression here. This expression can also be written using the sine function. To make this equal to this, we need a 2i out the front. It's also acceptable to say that I to the n sine pi kn on big N plus 1 is an eigenvector, because anything that differs by this by a constant scalar is also an eigenvector. For the rest of this presentation, we will stick to writing the eigenvectors in this form here. There's a loose end to be tidied up, either the long way or the short way. When we wrote down our finite difference equation, we gave the general form of the solutions provided the two roots of the characteristic equation were different. If the two roots were the same, then the general solution is of this form here. We've got our traditional solution here of phi 1 to the power of n, but we add to it another solution of n times phi 1 to the power of n. This only occurs in the special case of a repeated root. This fact comes from the theory of linear finite difference equations. For the solution of the finite difference equation to correspond to an eigenvector, we require both x0 and x at big N plus 1 to be 0. If x0 equals to 0, that immediately implies that our constant here b must be 0. Another possibility which we mentioned before is that phi 1 could itself be 0, but that would simply lead to x of n being 0 for all n, and therefore that does not give us an eigenvector. So we can assume that phi 1 equals phi 2, but that they are not equal to 0. In that case, then in order to get both x0 and x big N plus 1 to be equal to 0, first we require b equal to 0, which reduces the general solution to this form here. The scalar a, of course, just scales the eigenvector, so we can take a to be equal to 1 without loss of generality. But then we see that it's not possible to make this equal to 0 at little n equals to big N plus 1. Phi 1 is different from 0 if we want a non-trivial solution, and anything non-zero to the power of big N plus 1 will be non-zero, multiplied by big N plus 1 will remain non-zero. Therefore, there is no solution corresponding to the repeated root situation of phi 1 equaling phi 2. Unless, of course, phi 1 equals to 0, then we get the trivial vector x of n being all 0, which again is not an eigenvector. The faster way of tidying up this loose end is simply that we know there are at most n eigenvectors, and we've already found n of them, therefore we can't have any more solutions. Now that we have found the eigenvectors of Qn, we have to find the similarity transform that diagonalises Qn. This is so that we can ultimately compute the determinant of the skew-symmetric matrix we care about. Recall that we did this explicitly for the case of the Q2 matrix, and now we want to do it for an arbitrary Qn matrix. Because Qn is skew-symmetric, it is a normal matrix, and in particular the spectral theorem applies. Because the eigenvalues lambda, k are all distinct, that means the eigenvectors are automatically orthogonal to each other. This is a property of normal matrices and thus of skew-symmetric matrices. This means that our eigenvectors can simply be put together to form a matrix whose columns are orthogonal to each other. To make it unitary, we just have to normalize each of our eigenvectors so they have Euclidean length 1. Our kth eigenvector has got elements given by this expression here. We previously simplified this into a sine term, but for some calculations it's easier to leave it in the form of complex exponentials here. And we want to compute the Euclidean length of this eigenvector. So in particular, we want to work out the Euclidean length squared, which is the sum of the absolute value squared of each of the individual elements in here. Once we get the length of this vector, we can divide the vector by its length in order to make sure it's got length 1. The magnitude squared of a complex number is simply that number multiplied by its complex conjugate. The magnitude squared of xnk is therefore given by xnk multiplied by its complex conjugate. To take the complex conjugate of a complex exponential, we simply need to introduce a negative sign in front of the I for both these terms here because of the special form it has. So e to the I pi kn on big N plus 1 becomes e to the negative I pi kn on big N plus 1. And this term here, we replace the negative out the front with a positive. Again, we just multiply it by -1 to take the complex conjugate. Expanding out each term, we get that this is equal to this. The square of the Euclidean length of the kth eigenvector is therefore the sum of these magnitude squared, which is the sum as little n goes from 1 to big N, summing over the elements of the eigenvector of 1 plus 1 gives us 2. Take out the minus sign, we get that plus that term here. If we sum from 1 to big N, the number 2, we just get 2n. And we note that summing this term from 1 to big N and this term from 1 to big N is the same as summing just the first term from negative big N to positive big N, except that we get one extra term. So in this summation here, as little n goes from negative big N up to -1, we get all of these second terms here. And as little n goes from 1 to big N, we get all of these first terms here, but we get an extra term when little n equals to 0. When little n equals to 0, e to the 0 is 1, so this summation here will be 1 larger than what we want. Because we're subtracting this sum from 2n, that means that to compensate for this being 1 larger, we actually have to add 1 at the end here. So we're subtracting off a number that's 1 too big than what we want, so we add 1 to compensate. This can therefore be written as 2n plus 1 minus the summation in here, and the trick to computing summations of complex exponentials is to recognize that we can take the little n out and write this as some complex number to the power of n. In particular, that complex number alpha k is just e to the I 2 pi k on big N plus 1. To sum alpha to the power of n, where little n goes from negative big N to positive big N, we use the following trick. To see it, it helps to write this out explicitly. Alpha times s is therefore given by adding 1 to each of the powers of alpha. And now if we subtract this from this, we see s minus alpha s, where s is the value of the sum that we care about, is given by, well, s contains the term alpha to the negative n, which does not appear in alpha s, so it appears here. All the other terms in s get cancelled by some term in alpha s, and the only term in alpha s that is on its own, so to speak, that does not have a corresponding term in s is alpha to the power of big N plus 1. Therefore, we get s minus alpha s is alpha to the negative n minus alpha to the big N plus 1. Dividing both sides by 1 minus alpha shows us that the sum that we care about is given by alpha to the power of negative big N minus alpha to the power of big N plus 1, all divided by 1 minus alpha. Thus, the length of the kth eigenvector squared is equal to the sum of the magnitude squared of each of the individual elements, which we've shown can be written in this form here, where alpha k is e to the I 2 pi little k on big N plus 1. From the previous page, we know that we can evaluate this summation here. This summation is given by this expression here. So we simply need to substitute in our specific value for alpha k into the expression here. Now alpha k, due to its form, has the property that alpha k to the power of big N plus 1 is equal to 1. The reason is that k will be an integer. In fact, k is either 1, 2, 3, 4 up to big N. And e to the I 2 pi k on big N plus 1, if we raise that to the power of big N plus 1, we get e to the I 2 pi k. And if k is an integer, then e to the I 2 pi k is just the value 1. Indeed, e to the I 2 pi k is obtained by starting at the number 1 in the complex plane and going around the unit circle 2 pi k degrees. Each 2 pi degrees means we go once around the circle and return to our starting point, which is the number 1, and since k is an integer, we go an integer number of times around the unit circle, and thus we end up with 1. In this expression here then, we can replace alpha k to the power of big N plus 1 with 1, and by changing the negative sign to a positive sign, we flip these two around here to get this expression here. Lastly, because alpha k to the big N plus 1 is equal to 1, then alpha k to the power of negative big N can be written as alpha k to the power of negative n multiplied by alpha k to the power of big N plus 1, because the second term here is just 1. Combining these terms gives us alpha k to the power of negative n plus n plus 1, in other words alpha k to the 1, or simply alpha k. This term here is thus alpha k, so we have 1 minus alpha k divided by 1 minus alpha k, or just 1 here, so we end up with 2n plus 2. The Euclidean length of each eigenvector is the square root of 2n plus 2. The eigenvectors of Qn are given element-wise by this expression here. We put each element in to form the kth eigenvector here, and then we can form a matrix U of n by putting each eigenvector as a column of U of n. The eigenvectors are pairwise orthogonal, and so therefore the columns of U of n will be pairwise orthogonal. To make U of n unitary, we also require that each column has got unit length, and we computed the length of each eigenvector and found that they all had the same length, namely the square root of 2 big N plus 2. So by multiplying by this constant here, we have created a unitary matrix U of n. U of n Hermitian transpose times U of n is the identity matrix, and because the columns of U are the eigenvectors of Q, Q times U is just going to give us a matrix whose columns are again the eigenvectors of Q, but with each eigenvector scaled by its corresponding eigenvalue. We call the diagonal matrix, whose kth diagonal entry is the kth eigenvalue of Q of n, we call this matrix D of n. So we have Q times U equals U times D, the eigenvector equation, so to speak. And if we multiply this equation on the left-hand side by the Hermitian transpose of U, we get U Hermitian transpose times Q times U is equal to U Hermitian transpose times U is just the identity matrix because we arranged for it to be unitary. And so we're left with just this diagonal matrix D on the right-hand side. So we have found the similarity transform that diagonalises Q. While we initially looked at the special case of a 2x4 grid, it turns out that the expression we arrived at for the generating function that will tell us the number of tilings extends immediately to the more general case of a 2m by 2n grid. We are interested in computing the determinant of this expression here, that is the sum of two terms. The first term, which relates to vertical tiles, is the identity matrix chronicled with Q2m, and the second term, which concerns horizontal tiles, is Q of 2n chronicled with a matrix F of 2m, which is just a diagonal matrix whose diagonal entries alternate -1, 1, -1, and so forth. Our current goal is to evaluate this determinant, and we will do this by applying a similarity transform to ideally make this diagonal, but if that's not possible, then to make it approximately diagonal. We know that we can diagonalise the two Q terms by using the U matrix that we found. This motivates us to ask what we get if we apply U2n chronicled with U2m to this matrix here as a similarity transform. In particular, we want to know what we get if we have U2n chronicled with U2m Hermitian transpose times this matrix times U2n chronicled with U2m. We expand this termwise. The z here just comes out here, the z. This term, the corresponding one, will be U2n Hermitian transpose times the identity times U2n. Well, the identity doesn't change anything, so that's U Hermitian transpose times U. Because U is unitary, that's also the identity matrix. So we have the identity matrix here. Chronicled with, for this term here, we get U2m Hermitian transpose times Q2m times U2m. We know that U Hermitian transpose QU is a diagonal matrix whose diagonal elements are just the eigenvalues of Q, and we denote that matrix by D. Moving on to the second term in the summation, the Z prime comes out here. We have for the Q here, U Hermitian transpose QU. Again, we know that that is a diagonal matrix, which we denote by D. And for the second factor in the chronicle product, we have U Hermitian transpose times F times U. And it's only this term that is preventing this whole expression from being a diagonal matrix. We denote this matrix here, U Hermitian transpose FU, by G, and we claim that G is proportional to, it's equal to some constant times, the matrix with ones along the anti-diagonal. This is a somewhat remarkable result, because if F were almost any other matrix, we would end up with something very complicated in here, and this approach would not work. Recall that we wish to determine what U Hermitian transpose FU is equal to, where F is this matrix here, and U is this matrix here, whose elements are given by this expression here. Expanding this out shows us that this is equal to this. Our x's are eigenvectors of Q, and the product of F with U gives us a matrix whose columns we are going to call Y, and each element is given by this expression here, which is the same as for X, except that we alternate the sign on each row. So there's an extra -1 to the power of n in front of Y. That's the only way it differs from X. Performing this multiplication results in us having to compute X Hermitian transpose times one of the Y's. If we did not have this matrix here, then we'd have X Hermitian transpose times some other X, and because all the X's are orthogonal, we know that X Hermitian transpose times another X will be 0, while X Hermitian transpose times the same X will equal 2n plus 2, so when it's divided by this normalizing factor, we get 1. And that's why U Hermitian transpose U is equal to the identity. Having this matrix F in here changes the sign in here, and in general, it will be very difficult to calculate what X Hermitian transpose Y is for one of these X's and one of these Y's. However, we have actually seen this expression before when we were looking at solutions to our recurrence equation. We came to a point where we actually said we had two solutions because we were taking a square root, and we could either take the positive square root or the negative square root. And if we took the negative square root, we actually ended up with this expression here. And so that means that my y's are also eigenvectors of Q, which is quite remarkable. Because the y's are eigenvectors, that means that x Hermitian transpose times y is either equal to 0, unless x and y happen to be the same eigenvector, and then x Hermitian transpose times y is going to be equal to some scalar. Moreover, we calculated before that y1 is equivalent to the xnth eigenvector, y2 is equivalent to the xn-1th eigenvector, and so forth. We saw on the previous page that the columns of U are given by x1 up to xn. The columns of f times U are given by y1 up to yn. We will prove on the next page that the n plus 1 minus kth column of fu is equal to negative of the kth column of U. The consequence of this claim is that we can readily evaluate each element of the matrix UHFU. The element in the kth row and k''th column is given by this expression here, and we can now evaluate xk Hermitian transpose yk prime. We get down here that xk Hermitian transpose yk prime is equal to xk Hermitian transpose stays the same. The yk prime is the same as negative x big N plus 1 minus k prime. We already know how to evaluate a x Hermitian transpose times x because U Hermitian transpose U is the identity. The columns of U are xk, so this means that xk Hermitian transpose times xk prime is either equal to 0 if k and k prime are different eigenvectors are orthogonal to each other, and if k equals k prime, then we get an appropriate normalizing constant, in this case 2 big N plus 2. That's related to the Euclidean length that we calculated for each eigenvector that we're using. Put simply, we know that U Hermitian transpose U is the identity. We also know that U Hermitian transpose U is equal to this expression here without the f, which means this y is just x. So we know that 1 on 2 big N plus 2 times xk Hermitian transpose xk prime is either equal to 0 or 1, depending on whether k is equal to k prime or not. We therefore arrive at the fact that xk Hermitian transpose times yk prime is either equal to 0 in general, or if k plus k prime is equal to big N plus 1, then it's equal to negative in brackets 2 big N plus 2. Substituting this into here, we see that this matrix here is therefore largely 0, except on the anti-diagonal. When the row plus column sum to big N plus 1, then we get a negative 1 appearing here, coming from negative in brackets 2 big N plus 2 divided by 2 big N plus 2. We claim there is a relationship between the columns of U and the columns of f times U. Start with yn big N plus 1 minus k, substituting big N plus 1 minus k for k in this expression here gives us this expression. Note that we have got n plus 1 divided by n plus 1, so therefore in this term here that splits into e to the I pi n, and what's left over is e to the negative I pi k on big N plus 1 times n. Same for this term here, we have an n plus 1 divided by n plus 1, which gives us an e to the minus I pi n out the front here. E to the I pi n and e to the minus I pi n, because n is an integer, they are both equal to -1 to the power of n, which we can now take out the front. And finally, we notice if we compare this term here, it's just the negative of the term appearing in xnk here. The -1 to the n and the -I to the n, the two negatives cancel, so we just have I to the n. So we see that this expression is just the negative of xnk. This proves the claim on the previous page and allows us to conclude that U Hermitian transpose Fu is equal to a matrix with -1s along the antidiagonal. All that remains is to compute the determinant of this matrix here, where I is the identity matrix. The two D matrices are the eigenvalues of Un, where n is the subscript of D, and the G matrix has got -1s along the antidiagonal. This first matrix is diagonal, so that's straightforward, and this second matrix is block diagonal, where each block is antidiagonal. In greater detail, the first term gives us a diagonal matrix where we have a block structure with D2M repeating along the diagonal, and the second term gives us this block diagonal matrix where each block is antidiagonal and it's a constant number along the antidiagonal. If we just look at each individual block, we see each block has got the form, the D2M's give us a bunch of diagonal elements, and the second term gives us an antidiagonal structure with a constant number along the antidiagonal here. So if we can figure out the determinant of each individual block, then the determinant of the whole expression is just the products of all these blocks. If big M equals to 1, then the block structure just looks like this, and we can calculate the determinant using the straightforward rule that the determinant of a 2 by 2 matrix is this times this minus this times that. In the general case, the trick is that we can permute both the rows and the columns in the same way without changing the determinant. So what we do is we take the last row and bring it up to be the second row, and to bring the last column and move that across to be the second column. By doing the same permutation to both rows and columns, we do not change the determinant. Doing that changes this structure into this structure here, where we now have a 2 by 2 block in the upper left corner, and the rest of the matrix is just a smaller version of this. This means that we can use induction to prove that the determinant in the general case is going to be equal to this expression here. Indeed, the determinant of this is the determinant of the upper block, which we know from before is just this guy here, multiplied by the determinant of the lower block, but that's got the same structure as before, so we therefore just iterate and we get this product here. Because this matrix is block diagonal, its determinant is just the product of the determinant of each block. Each block contains a diagonal matrix and then an antidiagonal matrix with a constant number along the antidiagonal. The nth diagonal element of D2 big N is 2i cos pi little n divided by 2 big N plus 1. So this term corresponds to a particular diagonal element of this matrix here, and our G2M is an antidiagonal matrix with -1s along the antidiagonal. On the previous page, we deduced a formula for the determinant of such a matrix. We consider the elements of this diagonal matrix in pairs. We pair up the first element with the last element, the second element with the second last element, and so forth. We take the product over all such pairings, so because we have two big M elements, and we're considering them in pairs. We go halfway, little m goes from 1 to big M. The first term will be the product of each pair. So, for example, when little m equals to 1, we will multiply the very first element of this guy with the very last element of this guy, and that gives us this term and this term. In general, we pair up the mth term with the 2 big M plus 1 minus mth term here. As before, the elements of the D matrix are just the eigenvalues of the U matrix of the corresponding size. The constant anti-diagonal terms get squared, then subtracted from the first part of the expression. Every element of the first term gets multiplied by z, so when we multiply two elements of D together, we get a z squared. And similarly, z prime multiplies every element of this matrix here, so when we square a particular element, we also get a z prime squared. This expression simplifies. 2 times 2 gives us 4. I times I gives us -1, but we don't have a negative sign because this cosine term, by the property that cos of pi minus theta equals negative cos theta, this term is just the negative of this term. So the I squared gives us a -1, and negative cos of this second term is just the first term. So we get 4z squared, the first term cos all squared. The second term here also simplifies. 2 squared gives us 4, I squared gives us -1, which cancels that negative, so this becomes a plus sign, and we've got a cos squared here. Ultimately, we need to compute the Pfaffian, which is the square root of this determinant. So we want to try to write this expression here in terms of something squared, so we can take the square root easily. The trick is to recognize that as little n goes from 1 to 2 big N, this term here will be repeating values. By the fact that cos of pi minus theta equals negative cos theta, we see that if little n equals to 1, then this term gives us the same value as when little n is equal to 2 big N. And similarly, when little n equals to 2 and when little n is equal to 2 big N minus 1, we get the same value here and so forth. Formally then, we want to pair up this expression here with the case when little n is equal to 2 big N plus 1 minus little n. Specifically, we're going to change the summation from n equals 1 to 2 big N to just little n equals 1 to big N, and we're going to keep the first expression here, and then we multiply in the case when little n is equal to 2 big N plus 1 minus little n, which gives us the second half of our original product. Specifically, this term here is obtained from this term here simply by replacing little n with 2 big N plus 1 minus n. When little n equals to 1, this expression here gives us this corresponding to little n equals to 1, and this second expression here in brackets gives us this term here corresponding to when little n is equal to 2 big N. In this way, this product of these two terms is equivalent to our original product. The key point, though, is that by this property here, that cos of pi minus theta equals negative cos theta, we can rewrite this cos squared term as this cos squared term, and thus see that the second expression here is the same as the first expression here, so therefore this becomes a squared. We can therefore write this determinant as, in brackets, we take the square root of this number, so we have 4 to the big NM, the product of this first term here and then we just square everything. The Pfaffian is just the square root of the determinant, and so we just leave off the bracket and the square sign, and we get this formula here. And it's the generating function telling us how many tilings there are. And we recall from earlier that if we set both z and z prime equal to 1, then this expression will be the number of tilings. And if we simply remove z and z prime, which is the same as setting them equal to 1, then this formula here agrees with the formula we presented at the start.